Hey everyone, welcome back to the channel. So today we are going to explore some of the fundamental challenges faced by distributed systems. So those challenges are latency, failures and concurrency. So in the next 8 to 10 minutes I am going to break down these topics into understandable parts and explain you with the easiest way example possible and how these things create challenges in real world scenario. So this is our third video in the second section of our RGB system design playlist. We've already covered our first section with all these 4 videos. And we've already covered these two things in our playlist. So you can check out my RGB system design playlist where we discuss all the system design concepts in a proper structured manner and the easiest way possible. I try to explain it with all my understanding and with the best examples possible. Once you go through this playlist, you will be able to understand the entire system design concepts, real life use cases, and it will help you grab the concepts stronger. Alright, so this is our third video on the second section. So first let's just understand about what do we mean by distributed systems. So as I've already discussed in my previous videos, so distributed systems are networks of interconnected computers that work together to achieve a common goal or common functionality. However, with this distributed nature, some challenges come. So these challenges are latency, failures and concurrency. So each of these topics and challenges can significantly affect the system performance and reliability. So we need to understand them so that we'll be able to plan or and design our systems accordingly. Now first let's just discuss about the first challenge, that is called latency. So latency is the time delay that experienced during data transfer. For example, in a distributed environment, data often has to travel across different geographical location, right? Let's say my server one cluster is present here in India, for example, and my database cluster is present in Australia or US, for example. Just a rough example I'm giving. So this can introduce a delay when data is being transferred between these two clusters. For example, consider a, let's say, global banking application, okay, where a user in India is trying to access the data which is stored in US. Like that means the database stored in US, let's say. So due to this, physical distance and network congestion, the user might experience some kind of delay in getting the response and all. This is not just a matter of inconvenience. Even small delays can accumulate over time, and along with network congestion, it can drastically impact your user experience and overall system responsiveness. In order to solve these challenges, architects generally adopt the solutions of, let's say, caching, then content delivery networks or CDNs, and even replicating data closer to the user's location, which is known as edge servers also, right? So these are some of the techniques that system architects often use to reduce latency of the application. So my personal take in this is that, keeping in mind about the latency when designing system, it requires a balance between the performance of the application, the performance optimization that will get out of it, and the cost of the additional infrastructure. Because obviously, if you want to add a caching layer, or you want to add redundancy, or you want to add CDNs, or you want to add edge server, that will definitely add up to your cost. So you have to think about this trade-off and then accordingly plan and design like how to reduce latency in your application. So the next challenge that we usually face in a distributed system is the failures. So this is arguably, can say the most daunting challenges that most of the system architect face while designing system in a distributed systems. So in a complex network, individual components can fail, right? Let's say this server can fail. Unlike traditional single server system where we have, let's say, only one server in our cluster, instead of having cluster of 3 server for service one, we'll have, let's say, only one server in the traditional system. Unlike that, here in a distributed and replicated redundant introduced server cluster, if one node fails, it doesn't mean that the entire service will fail. Okay, however, it can lead to some kind of unpredictable data inconsistency and unavailability. For example, let's say if your database becomes unavailable, okay, let's say your master node becomes unavailable for some time, and there was a delay in spinning up a new master node for your database cluster. So there will be some delay which can lead to some data inconsistency between the replica nodes and the master nodes. So for example, you just think about an online e-commerce app, okay, during a high traffic sale event. Let's say Big Billion Day sale is going on in Flipkart. Okay. So if one server fails, it can cause a ripple effect, like which will disrupt the shopping experience for your users. And the load on your existing working nodes will increase, working servers will increase, the node in your working database node will increase, right? So it will drastically may block your system and slow down the performance of the system, which can in turn break the user experience of your users or your customers. Distributed systems are designed to handle such kind of cases gracefully. We do it via implementing redundancy, replication, and failover mechanisms. We have already discussed about this in brief in our previous videos, but in detail we are going to have separate videos for all of them. But this is just a part of the context, so that's why I'm bringing it up, okay? About the redundancy, replication, and failover mechanisms. System architect usually use techniques like RAPT or Paxos, right? Paxos algorithm, which ensures that even if one part of the system fails, okay, even if one part of the system fails, overall system remains reliable. A single node failure does not cause the entire services to be down. What I believe is planning for failure is not about being pessimistic or anything like that, okay? So it's an essential aspect of designing a robust system for your application. So accepting that a failure might happen anytime in your application and allowing us to plan the things and design the things accordingly. So it will, keep you ready for the unexpected failures that your servers might get or the systems might get, and it will make your system both resilient and scalable as well. So the third challenge that we usually face is about the concurrency. Concurrency is all about what? It's about handling multiple operations at the same point of time. And in a distributed system, concurrency is a major problem that we need to handle. If not handled properly, it will lead to multiple type of inconsistency. For example, when multiple users are accessing your application who are trying to modify the same data in your databases. All right, I'll give you an example. But let's say they are trying to modify the same data simultaneously at the same point of time. It can lead to different kind of race conditions and data inconsistency might occur. For example, let's take a example of net banking application. Wallet or a digital wallet application. When two persons are trying to, let's say, withdraw funds from the same account from two different devices, or let's say when two transactions attempt to withdraw funds from the same account concurrently in the same time. So if you don't have proper synchronization in place, the system might process the transactions maybe independently with the depleted balance, right? And it might lead to inconsistent balance in the account finally. Another thing is, let's say a big sale is going on in your application, okay? Ticket booking is going on, let's say about India versus Pakistan World Cup cricket match booking. You just imagine the situation. At the same amount of time, multiple lakhs of people will be trying to book the tickets in the application. They will be trying to book the same seat, and for a given seat, there will be 10 number of or hundreds of users who will be selecting that seat. So if proper locking mechanisms and those things are not in place, it might lead to duplicate booking as well as wrong bookings and all those things. So to manage concurrency, developers use various techniques such as locking mechanisms. That means once a particular ticket is seat is selected, let's just lock it for some amount of time for that user so that other cannot access it. All these kind of techniques are used to handle this type of concurrency related problem. So each method has its trade-offs definitely. So the optimistic choice or the optimal choice depends on largely on the specific use case, what use case you are going to employ, because you don't need to implement solutions for all the three problems. Maybe you might need or you might not need even. That depends on your use case. Now that we have covered the three major challenges, it's important to see how they interact. So in our previous past videos, we have already discussed about CAP theorem, right? Which is one of the foundational principles of distributed systems, which tells us that it is impossible to simultaneously guarantee consistency, availability, and partition tolerance. This means that in the situation or in the face of a network failure, partition tolerant, right? You must choose between consistency and availability. So if you don't know about CAP theorem, I'll suggest you to watch my CAP theorem video. So it is available in the RGB system design playlist. What does that mean? That means that balancing the trade-offs is where the design choices become both challenging and fascinating. So for instance, in a system where latency is critical, such as real-time gaming you are doing or financial trading platform you are doing, latency you cannot, afford to have latency in your application. Those are very crucial, right? So designers might favor availability and low latency over strict consistency. Their consistency or concurrency principles might not be needed to be handled, but latency reduction is a must thing there. Conversely, on the other hand, if you are designing some system where integrity is very much important for you, for example, like banking system, where data integrity and data consistency is the top notch and foremost thing that we need to handle. In those cases, we need to ensure concurrency. So we have to prioritize concurrency even at the cost of increased latency. Let's say the transaction are processing takes 5 seconds more, it doesn't matter. Latency is acceptable there, but concurrency has to be there. So with this example, I'm trying to give you an example of, I'm just trying to give you an overview of that. You might not need to solve all the problems for a given design or application, for a given system or application. It depends on your use cases. and you can prioritize one over the another based on your use cases and requirements. So to summarize, designing distributed systems is all about understanding and managing this kind of challenges and balancing the trade-offs between them. So latency impacts the speed at which data is delivered, which requires solutions like caching and data replication. So failures, as we discussed, are inevitable in any distributed systems that you design. And designing for failure means building in redundancy, and so concurrency, in the other hand, involves ensuring simultaneous operation do not lead to data conflict. Using locking mechanisms and all those things, we can ensure concurrency. So I hope this discussion has given you a clearer view of these three challenges. So thank you for watching. If you found this video helpful, please give it a like, subscribe to the channel, and share your thoughts and questions in the comment section. Let's have a healthy discussion there. So we are targeting to reach 3,000 subscribers by the end of this month, so keep supporting. Keep a tab on the RGB system design playlist. So thank you for watching this video, and I'll see you in the next one. Thank you.